Welcome to SIRM Triple YouTube channel. Let us discuss equal area criterion for stability, right? So it's a this topic comes under power system stability analysis and then swing equation. So a swing equation is a base for stability analysis, right? So ability to stable of the system. So if suppose motor rotor is swinging, or if suppose fluctuating occurs, so that's a disturbance we can call. So that we are going to take as a reference, and then we'll move on to the topic equal area criteria of stability. So this equation everyone familiar with, uh, right? Familiar with this equation, right? So this equation is called as a swing equation. This one is 2h delta d square delta by dt square. So here omega s is there, okay? Omega s, omega is equal to 2 pi f, so we'll get h by pi f, so this part, okay? And d square delta by dt square. Delta is the power angle, and t is the time taken for like swinging or whatever. Pa is the total power, accelerating power. Pm is the mechanical power output of the machine, and P is the electrical output of the machine. Pm is equal to what? T into omega, twisting force into omega. Omega is equal to what? 2 pi n by 60, right? And then P is equal to electrical output in the uh, conductor, armature conductor. So to examine the stability of the two machine system without solving the swing equation, the direct approach is called as equal area criteria. So swing equation also we have a different steps involved, and we are determining stability of the system. And even though equal area criteria for direct approach, it's a direct approach. So integration we are going to use, and then we are integrating two areas and then two parameters, and what happens, we will get a equal area criterion, right? So it's a concept. And equal area criteria continuation, there is a point P. This is a point P, okay? This is a point P close to the bus, this close to this bus. A three-phase fault occurs and cleared by the circuit breaker A after the short period of time. So this one is a circuit breaker, okay? This is a breaker, circuit breaker. So if suppose fault occurs, three-phase fault occurs and cleared by circuit breaker after the short period of time. See, basically circuit breaker is for to break the circuit when fault occurs. If suppose any abnormal condition occurs, automatically it will get trip off, and also it's automatic, and manually one 2 to 3 years back it would be operating, but at present if suppose fault occurs and then failure occurs, automatically that MCB will get again turned on. It's automatic process. So this will be that concept will be helpful for here. Thus the effective transmission system unaltered except while the fault is on. uh, if suppose fault is on, fault condition is occur, transmission system is unaltered, because there is a heavy current is flowing through the circuit, and then some damage will occur if suppose if you are altering. um, the short circuit caused by the fault is effectively at the bus end, so the electrical power output from the generator becomes zero until the fault is clear. So if suppose fault is till fault clearing, so generator voltage becomes zero. This is one single diagram for explaining power system components and power system equal area criteria and how the fault will occurs. So next there is the equal area criterion stability. To understand the physical condition before, during, after the fault. See here there is a different types of different conditions will be there in the fault. One is before, after, and then during the fault condition what about the current, and then after the clearing the fault current or fault what happens to the power system component, and before fault. So that we are going to study detailed here. Initially generator operates at a synchronous speed, right? So rotor angle is delta naught, and the input mechanical power is equal to output electrical power. Already I told you. So generator operates at a synchronous speed, constant speed, and that speed is always directly proportional to generated EMF, and rotor angle and the input mechanical power equal to output. So Pm and Pe almost equal, we will get it. And if Pm is not equal to Pe, definitely motor will not, generator or motor will not give proper output, right? Next we have a equilibrium criterion stability, Ft is equal to 0. So they have taken this three phase fault, okay, here. So initially like this, okay, condition, if some fault occurs, automatically it will be like this. And so this one is after fault, this one is during the fault, and before fault is one. A B C D E F G H they have given the condition of this one, delta B delta C also will be there. So this is a concept, so we are going to determine by using this graph, right? So the difference must be accounted for the rate of change of stored kinetic energy in these rotor masses. See here, in the rotor also we will get kinetic energy, because if suppose we switch on the power supply, so starting power is required, and if you switch off the power supply, suddenly what happens, inertia create, right? So it affected to rotor mass and then rotor speed also, and so that depends, right?